This is the answer key video for the topic 7.1 practice problems on the introduction to equilibrium. Okay, so again, we've talked about equilibrium at a very, very surface level in our other units. Okay, but this is actually where we get into this concept of equilibrium. Okay, so essentially here, equilibrium is talking about moving things forward and backwards. Okay, until at some point we reach a balance, right, where the products and reactants that are being formed and made are happening at the same rate. Okay, they're happening at the same rate. And again, it's called this dynamic equilibrium because things are moving. Okay, so it's not just that we reach a point and we stop, it's that we are constantly moving from reactants to products and products to reactants, right, back and forth. Okay, but we're happening at the same rate. Okay, and what I want to point out here is, again, with equilibrium, it's a double-sided arrow. Okay, you can see it like this with the two arrows. You can see it like that with the one arrow with the two heads. All right, both of those mean the same thing. Okay, the reaction is reversible. Okay, so that's what we mean, reversible. We can go from liquid to gas or gas to liquid. All right, and again, pointing out here, they're occurring at the same rate. It does not mean that they have to be the exact same concentration, okay? But what it means, again, is whatever I'm making, I'm also sending in the opposite direction, okay? So, again, to show here, concentration versus time, all right? Reactants and products, and again, they're not at the same concentration, okay? But what they do here is we reach a leveling out where we stop having net changes, okay? The products have the same concentration after our equilibrium point, and our reactants have the same concentration at and after our equilibrium point, okay? But again, there's a constant exchange of products and reactants. It's just that they're happening at the same rate, so again, there is no net change, okay? So if we look here at this balanced chemical reaction, okay, and again, that's one of the keys here is you have to make sure that it's a balanced chemical reaction. A plus 2B goes to C and D, or in the opposite, C plus D goes to 2B plus A, all right? What we can see here in what we're given says the reaction starts with 1 atm of A and 1 atm of B. So again, that means atmosphere. Okay, atmosphere. And why would we be talking about atmospheres or pressure? Because if you notice here, we're dealing with gases. All right. So again, please don't let that freak you out. You just have to know how to use those values. All right. But 1 atmosphere of A, 1 atmosphere of B, but there is no C or D in the flask. Okay, so sketch a graph to show the reaction as it proceeds to equilibrium. Upon reaching equilibrium, there is 0.8 atmospheres of A. Okay, so if we have our pressure or partial pressure versus time, okay, again, why would it be partial pressure? Because all of these are in the same container. Okay, so the total pressure is the summation of each of these partials. All right, now A and B both start at the same point, okay? And they are going to decrease. A is going to decrease to about roughly 0.8, okay? And if A decreases by 0.2, and again, how did I get 0.2? Because 1 minus 0.8 equals 0.2, all right? A, since it has a coefficient of 1, all right, it would be down by 1 of that. However, B has that 2. So B is going to lose twice as much as A. Okay, it's going to lose twice as much as A. All right, but on the flip side, C and D, okay, since they both have 1 coefficient, are going to gain the same amount, that 0.2. Okay, that 0.2. All right, and at the point where they have flattened out, which is roughly, about there, you could even argue maybe it's a little bit shifted that way, okay? But notice, again, it's flat, flat, flat. We have reached our equilibrium, okay? So again, the key there is obviously reading the question, knowing what you're starting with, okay, and then using our balanced chemical equation, right? Again, make sure you're watching the We Do videos and answering those questions. Now, question number 1 of the You Do's. Okay, looking at the reaction. Again, make sure it's balanced. 2 A's plus B goes to 3 C's. Okay, look at the model and the graph and answer the following questions. Okay, so if we look at this model here, A, we have 6 A's. All right, and we have 6 B's. So we start with the same concentration. All right, then it says if the initial mixture was A plus B, label the graph with A, B, and C. Okay, and the axes as concentration or time. All right, so this axis must be concentration and this axis must be time. Okay, then the question is, obviously we know that this is A and this is B. Okay, or both of these have to be A or B, but how do we know the difference? How do we know which one is which? All right, well, that goes to, again, our balanced chemical equation. What this is saying is we're going to use 2 times more A than B. Okay, we're going to use 2 times more A than we do B, which is why A is the lower of the 2 graphs because of this balanced chemical equation. All right, so this must be A, this must be B, and of course, C, since we didn't start with it, it's the only one that's at 0 and increases. All right. B, explain how you knew which line was A and which was B. Well, because of what we just said, A decreases by 2 times more than B because of the mole ratio from your balanced chemical equation. All right. Then complete the model at equilibrium. So lots of answers will vary. Okay, lots of answers could vary. All right, but what we should know here is if we look at equilibrium here, B has the highest concentration, then C, then A. Okay, so your model could look something like this. You could have more B, you could have more C, right? But really, if you look here, B should be the most, then C, then A. Okay, indicate on the graph where equilibrium has been reached. Okay, I think equilibrium is roughly about there. However, okay, it is just where the graphs have flattened. Okay, so you could potentially argue all the way up to maybe this line here. Okay, but again, be careful because to me it looks like this red line is still flattening out. Same with the blue line. Okay, so again, we're looking for where all of those concentrations flatten out. All right, number 2, the following chart indicates what happens over time following the addition of 1 mole to an empty 1 liter vessel. Okay, so obviously we start with our blue, and since it's empty, that means we have 0 of our red or our NO2. Okay, A says plot the data including title and label axes. Okay, so again, this is time and this is concentration. Again, an abbreviation for concentration is the bracket, so that is completely acceptable. All right, then from there, it becomes can you follow and plot, which again, I hope we all can do. All right, the blue line is going down because N2O4 is going to turn into our NO2. And then at some point right here at 10, okay, our concentration is 0.2, and then it remains 0.2. 1.6 remains 1.6. Okay, so again, it is not equilibrium between these two values. It is equilibrium at 10 because of what happens behind it, that it stays the same. All right, so our equilibrium is reached at 10 minutes. All right, so again, indicating on the graph, equilibrium is reached at 10 minutes. Not between 9 and 10, but when you see that value and that value does not change. Okay. Then, number 3, given this reaction, the partial pressure of the 3 gases were collected. So again, gases, you can use the exact same way as concentrations. All right, we've got our time from 0 to 6. Did the reaction reach equilibrium, and explain how we know? Well, if we've reached equilibrium, that means that the concentration is not changing or the pressure is not changing, okay? Or again, technically, right, the concentrations and pressures are changing, but they're changing at the same rate, so the values don't differ. So we basically go to our table and we say, are there any values that are the same? Well, in A, yes, there is, right? There. In B, is it at the same point? Yes. And at C, it's at the same point. Okay? So, since the concentration stopped changing at and after 4 minutes, we would say that we reached equilibrium at 4 minutes. Okay? Then the last one, number 4. Okay, write an equilibrium reaction for the following processes. Okay, so again, tying back into earlier units, right? We've got to remember how to write balanced chemical equations. We also got to remember, right, for example, what is sublimation? Right, that is a change of matter, right, going from a solid to a gas. Okay, a solid to a gas or a gas to a solid. All right, so I2, right, solid, equilibrium arrows, gas. Okay. Then B is a little bit more involved here. Okay. So again, you might have had to look some stuff up. Totally fine for right now. All right. But we have our HCN. Okay. With NH3. Right. Both of those are aqueous. We're going to have our double-sided arrow, and you should have looked up potentially, right, that it's going to become Cn minus and an NH4 plus. Okay, and we will talk more about this, but this is called an acid-base reaction. Okay, so our acid is going to donate its proton or hydrogen to the weak base. All right, and again, something to note here is that you don't see any charges on the left. So if you form charges on the right, we need to make sure that that -1 and +1 cancel out and we are balanced. Okay, but that is it. That's our introduction to equilibrium. So again, of course, if you have any questions, let me know. Otherwise, thanks, guys.